This video has been sponsored by Depstech, who provided us with a new endoscope to facilitate our restoration. Hello and welcome back. If you follow the channel, you know that we are involved in the restoration of an amazing mechanical analog computer from early fighter jets, the Bendix MG-1. This computer is one of the first iterations of an air data computer, a machine able to calculate all kinds of important parameters such as altitude, Mach number, air density and true airspeed of early supersonic jets. We opened it up and marveled at it in part 1, Master Ken explained how it works in part 2, and we did a deep dive on its synchros in part 3. We then powered up the temperature section in part 4 and rediscovered magnetic amplifiers in the process. In this episode, we are going to repair the entire thing, connect it to some instruments and test fly our new computer at supersonic speeds. Since last time, Ken has progressed a great deal in his reverse engineering of this ungainly electromechanical contraption. He has posted his findings in 2 detailed articles on his blog, which I'll link in the doodly-doo. But let me give you a quick overview of his findings. The air data computer has 4 analog inputs: the air temperature, which it senses via a platinum thermistor probe, the angle of attack, which it senses via a synchro, and 2 pressures, the static pressure and the pitot pressure, which gets sensed by 2 big black cylinders at the end of the computer. Each of these analog inputs gets transformed into a shaft rotation angle using servo mechanisms, more on this later. From there, calculations are effected by gears and cams. The basic calculating element is the differential gear, which takes 2 rotation inputs and provides a rotation output that is the angular sum of the 2 inputs. To make a multiplication, the log of the shaft angles is calculated using a logarithmic cam, then the logs are added using a differential gear, then an exponential cam is used to finally obtain the product. By adding a few scaling gears after the log cams, one can do square roots or other exponential calculations. Deformable plate cams with many adjustment screws are used to correct small errors and improve the computer's precision by fine-tuning. The outputs are also shaft angles, which are measured electrically by synchros and sometimes by potentiometers, and sent to instruments in the aircraft for display or to other navigation systems. The mechanical parts of the computer were in pretty good shape as they were kept clean in their sealed environment. Everything seemed to be moving smoothly as it should. The servo electronics, though, did not fare as well. All the servos work on a similar principle. An AC motor rotates a shaft until an error signal is zeroed, so that the resulting shaft angle faithfully represents the value of the monitored input. We went into the gory details of such a servoed pressure sensor when we repaired our Smith's pitot-static tester in a previous episode. Once the AC error signal is generated, an electronic servo amplifier is needed to drive the AC motor. All the power amplifiers in our air data computer use magnetic amplifiers, which we explained in episode 4 of this series. We already know that the one in the temperature sensor had failed. We traced it to corroded tantalum capacitors. So now that we succeeded in reviving the temperature servo section, the first order of business to get the rest of the computer to work is to check on the 3 other mag-amps. And that's the angle of attack sensor, and that's the second pressure sensor. Here's one that looks horrible right there. It's not even a cap, it's a resistor of some kind. Just look at that. So I don't think it's the resistor that's nasty, it's the cap that nastified everything around it. So it's this cap over here, and it rusted into that thing and rusted into that one. So this must have some interesting chemicals, and that one definitely isn't a cap anymore. And another one that's supposed to be 4 microfarad It is 1. It's trying. Right, so we end up with a bunch of capacitors that don't look good. The only ones that really tested bad are those 3 over here. So I removed most of them that were looking suspicious, although they tested good. This one, I recapped most of it, but I started to run out of capacitors. So this is recapped, but I ran out of 5 microfarad. Same here, I ran out of the 1.75 microfarad. And this is how many caps I replaced so far. Before we go try out our recapped amplifiers, let's acknowledge our sponsor Depstech, who provided us with their latest and greatest, the DS630. This endoscope has a new trick up its sleeve. It features a movable end tip, which you can control remotely from a big knob on the endoscope handle. That came in quite handy for this restoration. So we got a new toy, we got another Depstech. And this one is bigger. Can you take the thing off, Ken? And but it has a new trick. So instead of having 2 cameras like the other one, this one has the end thing that just moves. You can focus on it. It just goes weep, 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 weep. Weep. Weep.
Oh, this should be handy for seeing what gear is connected to what other gear way in the interior.
Oh, look at that.
The gears just keep on going.
I had one instrument where I had to come from the top and wanted to go look at the back, and I couldn't do it with the other one. And that would certainly do it. So here my feet, and here is my fingers. I am in there somewhere. There you go. Let's see, you can go, whoops. And then we can explore. Yeah, this is really very convenient. This is very aimable. Master Ken took a particular liking of our new Depstech toy, so he could explore the difficult to see gearing in the middle. That's also how we got the part numbers of the weird servo components located inside. It can also take pictures and record movies. However, I wish the frame rate and shutter speed were higher though, as there was a noticeable amount of rolling shutter in the recorded footage. We also had a lot of blurry pictures when we were not steady. We of course had some good pictures too. But apart from that, it's another instrument that we can easily recommend, link in the doodly-doo of course. Okay Ken, you're back.
So I've hooked up one of the pressure transducer servos. So this measures the pressure input and all the gears should turn based on the pressure. We're just using ambient air now, but it has a test relay. So we could switch in the test relay and it should turn to whatever the test pressure is.
Okay, and we have
our 115 volt 400 hertz inverter here.
So we don't know? Well, I recapped the thing, right? That's the amplifier I recapped. Okay.
So I put the recapped one in and took out the other one.
Okay. Oh. It moved.
Well, that's good. Should we try it again?
Try the test.
Okay.
See if it moves it to a different position. Okay, well, it works.
Let's see if it stops. At what point do we get nervous?
Yeah.
Right.
But your thing is just winding and not doing much.
Well, it's maybe going to altitude or descending.
Are you in constant current mode on purpose?
Oh, that's a problem. Yeah, you don't have enough power.
All right, we need more power here.
Yeah. Okay, we switch the power supply. Do it again. All right, now it has. There you go.
And then I'll switch it to the other relay.
Wow, it winds quite a bit, huh?
Yeah.
Okay, did it. And now if you don't switch to any relay, it's going to go to ambient?
Yeah.
Which is at the other end. Okay, I think we need to break out my monster Smith's machine and hook it up to a real pressure. Okay, it works!
I took off the capsule cover so you can see the pressure sensor here on these bellows, and if I just touch it, then the motors turn a bit.
So Master Ken, you wired yet one more thing?
Yeah, I hooked up one more of the servo amplifiers in the Bendix CADC. This one is for angle of attack input.
So which amplifier are you using?
So that is this one here.
Which we recapped, right?
Right. So the idea is to feed the plane's angle of attack in through a synchro, and then that turns gears internally to correspond to that angle of attack to provide a correction factor.
All right, does that work?
Well, let me move this a bit, and let's see if the gearing moves a bit.
It
So
does.
it's very sensitive. There, it moved to the new position. I tweak it a bit. It moves a little more.
So it affects pretty much everything in the calculation.
Right, because it will change the pressure input, which is your fundamental input to the whole system.
Mm-hmm.
And then if I move it too far, this friction clutch will start slipping, and then it just will never get into sync. Yeah, so now the clutch is slipping because I've gone too far.
Yeah.
So I'll send it back.
All right, so I have a customer return here. I changed some of the cap, but not all, because I ran out, and Ken just tested the servo amplifier for the second pressure input, and it doesn't work. So I guess I have a few more caps to change. I got them in the meantime. So these two are original. Check that I didn't miss any, but I think I changed all the tantalums and then a few other that
That looks good. We'll have to see if it works.
Yeah.
So let's power it up, see what happens. Sounds like something turning.
I hear some noises, but was it turning before?
I don't see anything turning.
Neither do I. Try to switch the amps, see if it's definitely sensing with the amp. So that's the amp that worked good on the other sensor, right?
Right. Okay. Let's see.
Yeah, this one
yeah,
works.
we're getting a lot more action here. You were right. The new recapped amp is
yeah, all the cap I removed, it tested good. So I think we probably have to do like we did for the other amp, make a harness and test it out of the machine.
Yep.
We kept testing and changing things in that amplifier without much success. Ken suspected that something was wrong with the very last stage, the mag amplifier. It was Eric who eventually found an unusual problem. Eric, you think you found the problem with Ken's mag amplifier?
I think so. I have the bad unit, the good unit. I checked them both on the LCR meter because I thought there might be something wrong with the capacitor here. This unit, we get about 4 microfarads each capacitor. The bad unit, I go to measure it and I measure 8 microfarads.
That's twice as good.
Twice as good. Well, no. What happened, I think, is that 2 capacitors shorted together. So we're seeing 2 capacitors in parallel instead of 2 separate capacitors.
How did that happen?
So if you look at this guy right here, there's a little slide mark on the metal here and here.
Oh, it got bumped forward.
So something bumped it and pushed it so that this terminal shorted against the terminal that goes to the capacitor underneath it.
Oh.
So then it turned two capacitors into one capacitor.
So that would explain also why the amp worked up to the mag amp section and the mag amp section didn't work.
Exactly.
Well, that would be nice. Okay. So we push it back and that might solve it.
Let's try it.
So we fixed the short and tried it again and it still didn't work. Ken eventually found yet an even more unusual problem. A bad brand new part. Alright, so we moved the capacitor and then it still didn't work, and after a little bit of back and forth and more bad capacitors, so actually we had a new bad capacitor. So yeah. There's an Amazon capacitor that didn't make it, so replace the old with the new, but the new was bad. And now, Mr. Ken?
So after great effort, we finally got this amplifier to work. If I power it on, we have spinning gears.
Excellent. So we should have the two pressure sensors working, right?
Right.
So we finally have the temperature, angle of attack, and the two pressure inputs working. All the rest should be done by the gears. Time to break out the Smith's pitot-static tester and give it some pressures. There's just a problem: we need to power the tester with 3-phase 400 Hz AC. But as luck would have it, Mike just got a flown Apollo Block 2 inverter to replace our hopelessly contaminated Block 1. And it sorta kind of works sometimes. It did, but I didn't. Aha!
Hello?
It's on the bench right now. What about some Apollo Yankee power to feed our British tester? Well, it looks like Mike's inverter is regaining its composure. Starts right off the bat, and I have hooked it up with a preliminary temporary setup to our British Smith's pitot test set. Let's gain some altitude. Open this one. There we go. And that is in turn hooked up to the air data computer. This is beautiful tube. I turn that on. Oh yeah. Things spinning in there, although it's hard to see. You hear it more than you see it. We need to hook up some instruments there. But let's fly a little faster. I can see all the gears spinning from my angle. Alright, my next company, CuriousMarc's Aerospace Steamworks Industries, is shipping up. Now we just need to hook up some cockpit instruments to our computer to visualize the results. So I rounded up a whole bunch of very cheap and very broken vintage instruments from eBay, and we started to reverse engineer and repair them. It turns out these instruments are beautifully made, but they are no two the same, and there is no free-floating documentation about them either. But in general, they work on very similar principle to our air data computer, with synchros, air detectors, and amplifiers. Some are AC, some are DC, some take 115 volts, 400 Hz AC, some take 26 volt, 400 Hz AC. It's a whole zoo of incompatible instruments out there. So what am I doing, Master Ken?
Well, we've got the CADC pretty much working, so now we're hooking up the instruments. We want our gauges, we have our angle of attack input, we have our temperature probe input, so we can make it actually go through its paces.
Much later.
You have it all hooked up now?
Yeah, we've got instruments hooked up, we've got it working. So I'll go over what we have. We have the platinum temperature probe, we have an angle of attack input, We have the two pressure inputs. We have an altimeter, we have true airspeed, we have the Mach number, and we have the total air temperature.
You're right, and those are sort of the correct instruments, but the indication will be off. The actual value will be not correct.
Yeah, the synchro values and scales from the instruments don't match the computer, so the numbers are semi-random.
So you want to turn your contraption on, and then I'll turn mine on.
Power everything up. We have a whole stack of power supplies here. There we go.
Okay.
I'll take our platinum temperature probe and put it into some ice water.
And I should look there.
The temperature is dropping.
It's working.
And then if I put it into the hot water, it goes up.
Yeah, let me try to get the gear. So hold it there. I think those are the gears over there. Make it go cold. Yeah, I can see them moving, and make it go hot again. It's calculating.
And this is the total air temperature, which isn't the temperature you'd find outside the aircraft, but adds the heating from the motion of the aircraft compressing the air.
Yes.
So it has to do calculations from what the probe measures to what the temperature really is.
Okay, so now it's my turn to spring to action, and I have pitot pressure and static air pressure, and I also have a little mechanical altimeter here. And I turn this one on. We are going to pick up altitude without picking up any speed. So for that, I'll open this one and get into here, and we'll start pumping. Is that working?
No, we're looking dead. The altitude is dead.
Okay, let's fix the altitude.
Wait, I fixed it.
What did you do?
I just jiggled it a bit.
Yeah.
Yep, we're good now.
Yeah. So this is complicated. This goes to so many instruments, and there's DC, AC at all kind of voltages, and DC at all kind of voltages going through it. Try again. So I'm going to close that, open this, and gain a few feet. There we go. So I'm going to pump it high enough that we go to like 20 or 30,000 feet, some kind of reasonable altitude to fly at Mach something. Okay, 30,000 feet. Okay, now close that. So if I change to my pitot altitude and close that, open this is so completely manual. Now I can get the Mach calculation going. Mach number, and yeah, you can see now it's doing it correctly. And then there is even better, you have the angle of attack, which changes absolutely everything.
If I turn this, we get a lot of changes.
So it basically corrects everything, and that's something you couldn't do with just regular instrument. You have to calculate it. Keep changing it. I'll see if I can get some of the gears. And then you see some gear movement over there. Keep going, keep going. You're just calculating all over.
So this is basically a correction factor for the static pressure, which then influences the other instruments.
So here you go, mechanical computing. Nice work, Master Kid.
That was a long
that was
time
quite,
to get to this,
yeah,
this
quite a
stage.
restoration, and then we had to restore all the instrument. That took forever too. And here you go. I would have never guessed that this black lump of metal was hiding this jewel of analog mechanical computing on which the best of our supersonic fighter planes depended. Never underestimate the calculating power of the gear. I'll let you admire a few more shots of our restored Bendix MG1 in action, and hopefully see you in the next episode.